This video will give a brief overview of the steps taken to restore a hedgerow condition Air Ministry Test Set 43 oscilloscope to a fully working condition. The radar room prefers equipment in good working condition rather than simply concerning itself to achieve a cosmetically perfect look to something that either doesn't work or works in a manner that's of no practical use for demonstration purposes. This is the top of the metal case. As you can see, it's in a pretty dire condition. The label is almost totally untrue, as the inside looked like a small explosion had gone off inside. With the tube removed, there were loose wires and components hanging off in all directions. With no schematic diagram of the modified set, there'd be zero chance of using any of the current circuitry, so a total teardown was going to be necessary. These shots show the inside stripped down, with many of the parts found to the inside to the right. These include a completely strangely wired up transformer power supply setup containing a total of 3 large transformers, one on top and 2 underneath, plus 2 large chokes. The front panel here seems to be covered with a film of muck from many years' storage. The chassis underside, however, was reasonably clean. The front panel took a long time to clean up, but after stripping it down was deemed to be in acceptable condition to simply do a rebuild. We started off by fitting the high voltage controls to the left of the panel with the brightness, focus, X and Y shifts on a separate Paxlin panel on standoffs as per the original. The power supply was next, retaining one of the transformers you can see. A PY31 rectifier was mounted in between the two and a small heater transformer behind it for its sole usage. Here we have the underside of the power supply. At this point we must be extremely cautious because we have mains coming in here. All this is live when we turn it on, so one must be extremely careful with what we do. What we're going to do first of all is simply check the positive HT supply. We've placed temporarily an electrolytic capacitor across the output of the rectifier valve so we can actually see what the rectified DC will be rather than the half wave unrectified, which will give us a completely different reading. So what I'll do now is I'll turn it on and we'll put the probe on and wait for the valve to warm up. That's it, we have powers on it, we must be careful. We're now waiting for the valve to warm up. So here we go. Right, that tells us that we have about, according to that, 334 volts DC across the capacitor. Here is the new power supply module fitted to the back of the main chassis. The notes on this A4 sheet show the wiring up of the power supply to the CRT from the main circuit diagram to both HT plus and HT minus, with those connected in. These provide the voltages for a spot and adjustments on the CRT screen. The components seen on the sketch are in fact those which are to be fitted next. This is a circuit which we've completed. Very simple, nothing unusual about it. You can see at the bottom 3 transformers, one as I already explained, which is 17 volts for the PY31 rectifier. That is for the halfway rectification for the currently 334 volts offload. 2 smoothing capacitors, a smoothing choke, they're underneath the board. Here we have the 5 volts. The 5 volts here plus 2 dropper resistors feeds the tail of the cathode ray tube and also the VR78, which need 4 volts on the heaters. This is to do a nice blanking signal, because leaving the diode out there means that when you turn down the brightness you can have a bright spot at one end and it gradually tails off as you reach the other. But put the diode valve in here and you have a nice even spot. So that's that. That's the 20 volts, there's the 250, and the 700 volts is in fact, this is in fact a 350 plus 350 volt mains transformer. So we've removed the center tap, we're not using that, taken one end down to earth, and we have 700 volts offload. And once we've rectified that, that takes it up to about just under 1000 volts. So if we add the 1000 volts to the minimum of about 300 volts here, that takes up about 1200, 1300 volts for the tube, which is just what it's looking for. You can see the three diodes here. We put three 1N4007s in a row, just redundancy there really, and that gives us, that rectifies the 700 volts in the transformer. Two of these large capacitors, which are actually at the back of the set, both of those are rated at 2000 volts each, and that gives us our negative supply. Then obviously you have the chain here of the brilliance control, focus control, the 1 mega ohm resistor, and now we're up to ground. The little bit up here which we've incorporated so far is actually the HT, which we split in half, and that then is taken. This is the one I forgot to connect up that wire, the conformal coating A3 and A1 anodes, and that's it. That's all there is at the moment, but at least that means the HT is done. We have the HT supply. Also we have the EHT, which is a negative voltage, and the next job after this is all working, we can move on to starting the time base. Quick few points about here. So here we have the PY31 rectifier. That's for rectifying the positive HT voltage. Two big capacitors behind. You can see these two are the smoothing the negative EHT. This is our transformer that's giving us 700 volts and 5 volts, which is dropped for the tube filament, and 6.3 is our second 6.3 volt supply. This is the HT, which is currently giving us 334 on the positive rail. That will drop obviously a bit when we start drawing current from it. The little transformer in the middle there gives 17 volts for the heater on this. The diode you see on the back of the capacitors there is to give us that nice clean flyback spot removal. These roughly tacked on wires here are simply connecting the X and the Y plates together to take them up to the same level as A3 and A1, just so that we can have a spot on the screen. They will of course disappear off and they'll go to the various sections of the X and Y plate drivers. If we turn it on, hopefully we'll have a spot in due course. So there's nothing else. The X and Y shifts don't do anything because they're not connected through at the moment. That'll be the next job, will be to connect those up to give us shifts, and we have a spot. Turn up the brightness a bit. There we go, we have our spot. It's as bright as it goes. So it's quite a bright little spot. We don't want to burn a hole in the screen, so we'll turn him down. There we go. Nothing much more to show. That works. Nothing more we can do about it. The X and Y plates are not connected, so the spots should be roughly in the middle of the screen. One last update on the chassis. What we've done is we've connected up the X and Y plates through the shift pots here. A couple of trimmers at the back to make sure that we can shift everything around the screen just how much we want. This is the other side of the chassis, of course. Nothing much to see here either, but you can usefully, they put X and Y plate designations on the tube base, which is most unusual. Usually at best you end up with the numbers from 1 to 12. Anyway, there we go. There are four 2.7 mega ohm resistors. They go on the pins. These screen wires here are coming from the pots for adjusting the shifts for the X and Y, and then we'll be taking other connections off actually on the plates themselves to go to the time base and the Y amp. All four of these should work. We have the brightness, focus, Y shift and the X shift, and strictly speaking they should work. And then we have a spot. We're going to make it small, and we keep it small for a short period of time. Y shift, yep, there we go, that goes from top to the bottom, and the X shift, same again, side to side. So that's about it. Probably best to leave it as a bigger spot to not damage the screen. With the EHT and trace shift controls now working, we can now concentrate on assembling the X-axis circuitry. First of all, here's a better picture of the completed front panel with all the controls and sockets fitted. We've decided to fit B and C connectors to make the equipment more compatible with today's scope probes, etc. Original Pi coaxial connectors tend to be rather expensive and hard to come by these days, but we do try at least to use these on most of our 40s rebuilds where we're making up bespoke connecting cables. I believe that the large mains on-off light was in fact the same type fitted to the instrument panels of a number of 40s era aircraft. Here we see the main time-based switching board with the timing capacitors and the wafer switch. This will soon be connected to a knob on the front panel via a remote control shaft. Right, in front of you see this is the time-based board with the time-based capacitors, 2 sets and the switch and the remote shaft going to the front panel. Valves wise, we now have a VR65, which is at the end here. That's the commercial equivalent, was the SP61 of course. Down here, hidden down here, is a metal American valve. This is our double triode, which we're going to use for two parts of the circuit. In front of it is a VR54, which is a double diode. And at the front there's a classic red encapsulated EF36, which is by Mullard. Now this one is the only modern valve amongst the four, and what we'll be doing is changing this one for a military equivalent in its grey livery. Haven't done that yet. Here we have the underside of the chassis. You can see there's a big block here which we've done. The piece here obviously is going to be the Y amplifiers, and so far we haven't put any valves in or any components. The wiring for this, you'll notice that because this is an old restored chassis, or to be restored should I say, I'm trying to use older components if possible. So obviously after checking the values of these resistors, they're within spec, the capacitors are fine for leakage, etc. That's why it looks sort of quite old on there. Obviously you spot new components here and there. That's when we've had to put new ones in. So if we start testing the first part of it, this is going to be the X amplifier. Now this is the input to the X amplifier here. What we're doing, as we happen to have it conveniently close by, is we're taking a feed from the calibration output of the oscilloscope feeding into the X. This is a 2 volt peak to peak signal, and this one here is the scope probe, is looking at the output of the amplifier. So first of all we look at the trace actually on the scope. As you can see here we have 2 divisions. They're 1 volt per division, which means that's what's going in, and there you can see is the takeoff which we're using to go into the X input. If we now remove the scope probe from here and put it on the back end of the gain control, that's the X gain, we've hooked it on there. What we're doing now is the signal still going in to the X amp, going through the X amp, and it's coming out on the slider of the X amp control. So let's have a look at it on the oscilloscope. Okay, so there's nothing on the scope yet. So if we now advance the gain, there we go. So that would be 2 volts peak to peak, and it's gone right off the scale. So that's 10 volts per division, so we're talking about 1, 2, it's about 25 volts. So there's 25 volts coming out. So that's proving our X amp works okay. We have 2 scope probes now attached, both going to 2 inputs on the oscilloscope. We have the X amp output here, which is X1, and the second one is actually going to the inverse because the triode is being used as an inverter to feed the X2 plates. So what we'll do is we'll look on the scope and check that we have an inverse of whatever's coming out of the first one. Well, that's a good start. We have on the first trace a reasonable looking waveform there. If we adjust the fine adjustment, yep, seems okay, and the coarse adjustment, let's try that. That should be blank because that's for X and Y separately. Let's look at the top one. That's not too bad. A little bit of a blip at the top, but that's of no consequence really. Fine, so the idea now, as we have both scope probes connected up, is to adjust the scope to give us a second trace. Just a minute, I seem to remember I left that one on ×1. That's better. So there we go. One is slightly smaller than the other. That was the out of count. a slight curve in here, but then if we invert it, yeah, it's not perfect, is it? Now that we've wired up the front panel, what we're going to do is test the sync input. That's the external sync input that goes in through that terminal there. We do this quite easily. The signal here is coming from the scope calibration output, as we've used before, and what we'll do is see if we can synchronize the time base we've just finished building in here with the synchronization signal. So let's have a look at the test oscilloscope and see what we can see on that. Very simple test here. We can see the time base running free. So we adjust it, there we go. That's the time base running free. And on channel 2 we can see the calibration output. We're just simply looking at that, showing what's coming out of the oscilloscope here. So if we turn on the sync to external sync, we'll see what happens. That's it. Nothing more to say, it looks like it's locked on it. If we try and come off frequency with that, that's adjusting the time base fine. Seems quite a good range, doesn't it? That's it there. So we turn off the sync again. Yes, that's quite off frequency, isn't it? There we go, so I reckon our sync amp works fine. With the X plates circuitry all done, we've stopped briefly at this part here, which is the Y driver. We have the two capacitors feeding the two Y plates and the driver triode, and then we have the last amplifier, which is a pentode, so it's a triode pentode, and that will enable us to put a waveform into it to have a look and see what it appears like on the screen. Now, interestingly enough, this is a PCF 802. I happen to have a couple of these lying around. It's a relatively modern valve. Perhaps it's one of the last commercial valves for television produced. It's quite recent. So we decided to use that, as it happened to be one. Now, the problem with the PCF means that it has actually a 9-volt filament. Now, there's no problem with 9 volts because we already have 12. We already have 6.3. So drop a resistor from the 12 volts over here gives us the 9 volts we need. Let's have a look at the circuitry itself in the chassis. Not very much to see here. This is just simply the bottom of the B9A valve holder with the associated components for that bit of circuitry we showed, including another one of these boards here, just which we can put components on. Here we can see the chassis is upside down, of course. There is the PCF 802, which is hanging upside down at the moment at the back end of the chassis. Here we have a 10 Hz signal. It's not locking on the synchronization coming in through the screwdriver there. There's no internal sync circuitry yet, therefore we're using the external sync socket. Move up to 100 Hz. It's 100 Hz. See if we can lock on that and see if it works. Yeah, it's locked on that. That's 100 Hz. 1 kilohertz. Seems to be locking quite well on that, doesn't it? So that's 1 kilohertz. 10 kilohertz. That's quite good. And if we now wind this up to the maximum this oscillator will do, let's stop at 50 kilohertz. Now that's 50 kilohertz. That's not too bad. 50 kilohertz, and the highest this will go to is 100. There you go, that's 100 kilohertz. There we go. I think that's about all we can show about the rebuild of our test set 43, though at this point there are a few minor niggles to be investigated and sorted out. Here are a few images of the finished chassis without the tube to make the circuitry easy to see. As you can see, the final valve lineup consists of 10 valves if you include the diodes and the rectifier. The only reason why we didn't use an EHT rectifier, as opposed to using a silicon one, was we didn't have the spare LT winding and would have had yet another transformer underneath the chassis in order to provide one. The tube used is in fact one of the popular VCR 138 models, the same type as used in both our H2S radar monitor 28 and our Air Ministry test set 73. The last clip is showing the newly completed test set 43 displaying lithogist patterns using the output of our oscillator that just happened to be still on the bench. I hope this video gives you some idea just how much work is needed to bring equipment such as this back into a good working condition from the ground up. Thanks for watching.